সিট চেঞ্জ করলে এখানে অ্যাপসটা
Can you hear me? Okay. Okay, very good. Very good morning to everyone. So today I will give you briefly on short and medium range numerical weather prediction for agrometrical advisory. So in a brief introduction, I want to tell, because there is various way of weather prediction, but I will focus in this 1 hour on mainly on the numerical weather prediction. And as you know, numerical weather prediction is an initial value problem, and the forecast skill of the endorphin models depend on the quality of the initial conditions. Current improvements in numerical prediction of extreme weather events are mainly because in tropics, weather is generally stable. Day to day, summer means summer, winter means winter, and so on. But on the top of that, we have the extremes, which are the much more important, like tropical cyclone, thunderstorms, heat waves, cold waves, and so on. So therefore, current improvements in numerical prediction of extreme weather events are mainly due to the increase in model resolution. I will show that the improvement that is mainly due to increase of the model resolution. That is one of the factors. Improvement in physical parametrization schemes, which is the backbone of the model and most difficult and most because dynamics of the model is known, but physics is always needs the improvements. Enhancement in observation network and availability of data from various non-conventional platforms, because we have very less data coverage region, and we have the Bay of Bengal, Arabian Sea, Indian Ocean, and so on, which is the data sparse region. So we depend a lot on the non-conventional data also. Improvement in analysis and data assimilation techniques and enhancement in computing facilities also required. So these are the major things, and we have a lot of improvements in that, and that lead to the improvement in high impact extreme weather events in mesoscale convection. As you know, even 1904, Brzezinski has formulated for the first time that weather prediction as an initial problem for the hydrodynamic equations of the baroclinic fluid. Otherwise, actually, in 1855, first time the synaptic charts were developed in Paris Observatory. So prediction of weather systems are of broadly two types: subjective approach and objective approach. Under the subjective approach, mainly the synaptic methods, and which my colleague Dr. Pai will tell you about that, more details. Then there is the climate methods, which is based on the climatology of a long time. Like you go to conference symposia, you get the number, like you bring a coat because temperature is low, or you bring a umbrella because it will be so that is climatology. But I will tell focus on the objective approach. Objective approach also various types. Dynamical method, which I'm going to focus today, in numerical weather prediction. Besides that, we have statistical methods. India is a pioneer in statistical methods, as you know, in the world, because first time we started the seasonal forecast using the statistical methods, even before 1900. That is, but dynamical methods have its own limitations. Statistical methods also have own limitations. So therefore, many times we do dynamical statistical methods. That is of two types, like ppm and MOS. I will not cover that much. And now we have ensemble and super ensemble methods where we take multi-model combinations or one model with a different combination of physics or data. So we do ensemble and super ensemble approaches, and also we produce the probabilistic forecast and with uncertainty measures, as well as now IMD is giving also impact-based forecast. That means a decision support system for the different stakeholders. So if you see the science, that is the observation in the engineering aspects, understanding the science, modeling and prediction is the computer engineering process mainly. If you see the different processes in the topics with different scales and durations, it is, you see from bottom, it is dust bits, which is actually very short and very short space scale and short time scales. Tornado, microburst, thunderstorms, monsoon, hurricanes, warm fronts, extratropical cyclones, which cover the almost very large scale, and monsoon, which cover actually, as you know, almost 1/3 of the our globe and up to 4 months. So this is again representing the typical lifespans versus typical size of these systems. Small scale turbulence eddies, that from actually the weather starts from that planetary waves like westerly waves, as you know, it covers the entire globe, whereas it starts from the very small, few centimeter scale, small turbulent eddies. Then we have thunderstorms, then we have the land sea breezes, tropical cyclones, mid-altitude cyclones. And then if you see the temporal and spatial scale, they are broadly the following. Temporal scale, we have nowcasting, which is done in 0 to 24 hours, very short range, that is required for various purposes, particularly any activities you do in a particular day, but that is also equally important for the agriculture purpose, because if you want to use the sowing and there is a heavy rainfall, when you are doing sowing afternoon heavy rainfall, or you are putting pest and pesticides you are putting or fertilizer giving, then after that there is a rain afternoon, suppose morning you have done. So nowcasting is used for very short plan of the agriculture, particularly sowing, applying the fertilizers or pest. Short range 1 to 3 days forecast. So that gives again similar type of things. If you do something, you need what will happen, so that to settle down the things, it need 1 to 3 days. But then we have seen for harvesting, then taking the crops to the safe place and protecting the crops, we need also medium range forecast 3 to 7 days. Again, 3 to 7 days planning you can do actually for the irrigation purpose, whether you go for irrigation or not, because if there is rain in 3 to 7 days period, you may not go for the irrigations. And so that's why, or you want to harvest it and bring the crop to your safer place, to go down or something. So you need a medium range forecast. Similarly, extended range forecast 7 to days 1 month, and that is our friend Dr. Sahai is going to present you. And long range forecast, that is actually Dr. Pai also going to tell you that seasonal scale forecast, month to season. So these are the different forecasts that is generated in India, which I will focus. I will not go to global view. I will tell you what are the products available, so that you can use it for your various applications. Similarly, spatial scales, we start with the turbulence scale, I told. Then we have meso scale process like convection, thunderstorms. We have synoptical process like cyclones and anticyclones. Then we have the large scale process like monsoon, jet streams, planetary waves, and so on. So if you see, we call it seamless suite of simulations. That is what is done in our weather prediction centers, particularly National Center for Media and Weather Forecast, NCMWF, and in Indian Institute of Tropical Meteorology. These are the two major organizations in India. They are doing predictions for application, and IMD, the nodal agency, make the Labanshu, any problem? Please. Please, I request all the participants, everybody, please mute their systems so that you can clearly understand what I'm telling you.
Nabanshu, you can actually put off. You are a host, no? You can do that. Mr. Vishal.
The forecast is broadly categorized in 3 ways. One is the initial conditions and weather predictions. It starts from minutes to hours to day to a week. So that we do by nowcasting, short prediction, and medium forecast, which I will cover in my talk. Then we have the climate scale prediction, that is week to few weeks to month, that we cover. Then we go to the scale of climate change and so on, and climate prediction and the seasonal scale. So these 3 topics is covered by actually our 3 experts for you today morning. So please be attentive, and if you have any problem, you can ask us, but don't talk or don't open the mic when we are speaking. So it should not digress us. So if you see that, as I told, weather prediction aspect is the problem which I am going to cover, and I told why it is important for the agriculture. Even if you see the schematic diagram for the lead time for schemes, so if you do nowcasting or short range or medium range of 5 days, your forecast scale is quite high. But as you go in a month or a few weeks to a month, the forecast became more difficult because memory of the model cannot take up to that period. But then when you go to seasonal scale forecast, then we have also some skill is better than if we make a week or 2 weeks, but we have also improved that by numerical method nowadays. So I'll tell the most skilled forecast is that is few days up to a week or so. Application of weather forecast in various sectors is required, as you know already, perhaps. So most important sector is the food security. Food security, agriculture, horticulture, poultry, and fishery. So these sectors, we apply the weather prediction extensively. Starting from the day-to-day activity, that to planning, and that to also maintaining and getting a sustainable production of foods is the most important. And the weather application, weather and climate is very much used in this sector, that is what we call agrometeorology, which classes you are taking. Similarly, it is a very useful for the water resources like water management, dam management, irrigation, so on, transportation, defense services, industrial mining, clean energy, health, communication, tourism, and disaster mitigation and management. So the major components of a numerical weather prediction, if you see, they are the following. First is the initial condition and boundary conditions, which we get from data assimilations. And we have different type of data assimilation there. We have 3D data assimilation, 3D WAR, we call 4D WAR is there, and ENKP there. Similarly, we should do the sensitivity experiments with the data. So I'll come a little bit as I move further. The second comes the dynamics and physics of the model. And in that, we see mainly what will be the resolution, whether it's a large scale model or a regular model or mesoscale model. Depending upon that, we make the resolution of the model, and then parameters of physical processes. And that is also equally important, because I will come to that. Ultimately, you need a forecast, which actually you have to use. The model products, first we do the systematic diagnostic of the models. We see what is the bias of the models, we make bias corrections. Then we go to location-specific forecasts from the model outputs, and ultimately we do probabilistic prediction. That means what is the possibility of the things will occur. That means a rain will be there in afternoon heavy, whether it is 80% or it is 50% or it is 10%. So people take action accordingly. And ultimately, also now I am doing last point I want to give in that decision support systems through impact-based prediction. So now India also started impact-based prediction, which depend upon the economy, social status, and intents of the systems. They decide that what will be impact on the users, and based on that, they give a decision support system so that end users can do the decision based on the prediction in different sectors of their activities. So first, as I told, basically the observations, and we have, because you see that weather have no boundary, so we cannot do one region. Like Nepal, we cannot do our model unless we get data surrounding us. We cannot do Bangladesh, or we cannot do India if we cannot get data from our surrounding region. So therefore, you know that we have a WME there, which facilitate the observation from various sources. And we have now launched GOS, Global Earth Observation Systems, where satellites play a very important role. Besides that, we have the Doppler radars for the mesoscale things. Then we have the AWS, GPS, and so on. Then next thing, like once data is collected, how it is transmitted and processed. Because data cannot be transmitted as it is, and WMO set up a thing in consultation with the different country, all the countries, and that is what we call DTS. Then once data is obtained, we have to do data assimilation, then we do model integration. Then after that, we customize for the end users, and then dissemination of and early warning systems, that is what I told you. Then effective disaster management and mitigation strategies, adaptation strategies in climate change scenarios, because as you know, in climate change scenario, though it is a change is very small, but it has a large impact with the intensity and frequency of the different type of disasters, mainly hydrometeorological disasters. So this is a just pictorial view of the initial value problems that you weather prediction from different sources, that you can see that actually 2/3 of the area we don't have any land surface. It is ocean surface, or it is mountains or deserts where we cannot take observation. It is very difficult. So satellite plays a very important role, and we have two types of satellites. One is geostationary satellite, which is fixed and at a particular longitude, and another is that polar orbiting satellite. So geostationary satellite gives continuously your observations. That's a good thing, but it cover only maximum. It will cover only 90 degrees of the whole 360 degree of the globe. So only one sector. But whereas a polar orbiting satellite, it can cover the entire globe because it will move around the globe. But only the disadvantage that you will not get continuously the data. You may get once in 3 days, one in 5 days, or one in 11 days, and so on. Besides that, we depend heavily on the surface observations, and most important surface observation is your radio sound, that is RSRW radio sound or GPS sound is there, which give the vertical profiles of all the 5 meteorological parameters that we need for the models or prediction purpose of any type. Besides that, we have the AWS and many other things are there. Perhaps part of that will cover by my next presenter, Dr. Pai. And this polar orbiting satellite, as I told, it covers the entire globe, and it goes covering the polar regions, ocean regions, and so on. It covers entire part. And then this is the GTS system that transmit the data and make it available, because short and medium range forecast heavily depend on the data. And within 3 hours or so, all the data obtained from any part of the world is available at any point of the place, so that your data is available thanks to the WMO and cooperation of all the countries. Then we come to numerical weather prediction, that is dynamical methods, which I'm going to cover. So it is a very complex system, as you know, atmosphere, because it has a lithosphere, cryosphere, hydrosphere, biosphere, atmosphere, and solar system outer space. They all are interactive. Just like there is no boundary we have in the horizontal around the globe. Vertically also, we have all the things they interact. Biosphere, suppose like our agriculture biosphere, they provide the soil moisture and so on. I'll show you that plays very important role. It is not that weather affect the biosphere, like our plant and vegetation, but plant and vegetation also affect our atmosphere equally. And there are scale of interaction of different scales, and it may not be possible for me cover in short time. Then what region will take. Like a thunderstorm, it occurs for a few minutes to a maximum 1 hour. So for that, we don't need a global model. And similarly, heat wave and so on. So if it is a short-term phenomena of a one-day phenomena, then we took a region that is first circle that you are not in inner one. But if you want 2 to 3 days, then you go to little large region. But if you go beyond the 3 days forecast, like you want a forecast, you want a cyclone moving for 7 days or so, then in that case, you have to take a large global models. If you see the framework of the model, it will depend upon the observations, and we have 7 variables. Any model you take, any dynamical framework you take for prediction, it will depend upon 7 variables. Most important is your pressure in tropics. Most important again, wind, velocity and vector, which give us zonal, meridional and vertical winds, temperature, density and specific humidity. But we don't measure density, rho, because that comes from a mathematical relation. Many times we don't measure the vertical velocity because that is also very difficult and it has a vertical compensation. So we measure only 5 parameters, that is pressure, temperature, humidity and wind. They are broadly of 2 categories. Wind is the motion vector, motion aspect, and pressure, temperature, density, that is the mass aspect. So we have mass and motion, and therefore they conserve by, and atmosphere is a fluid, so they conserve by classical physical principles of hydrodynamics and thermodynamics. Dynamical model, again, I will not tell you all details, that you can get my PPTs. Then why do we need the models? Because the governing equations are impossible to solve. Approximate and idealized set of equations are necessary. And when you are making the approximation, we are guided by the 2 principles. We want to choose the simplest model possible. At the same time, the model must be efficient enough in terms of computer demands. And the model are only simplified representation of maps of the reality, a tool to represent the data of the real world. The main purpose of a model is not to feed the data, but to sharpen the equations so that we can get a better prediction of the variables. So first weather prediction was started with numerical methods in 1950s. Then at that time we are thinking about atmosphere, then land, then comes ocean, then comes ice, then comes the aerosols and the greenhouse gases and atmospheric chemistry. So these are the developments. So weather prediction is not a very old problem. The problem of only last 70 or 75 years. So these are the basic equations. They are based on, you see that the simple physical laws, classical physics, conservation of momentum that give you the U and V component or W components. We have conservation of energy that gives you the temperature. We have conservation of mass that give you the density, is represented as vertical velocity you can get from. Then we have a conservation of water equation, which gives us the water vapor in the atmosphere. Then we have the equation of state, which gives us the rho, which we are not measuring in the atmosphere, from pressure and temperature. So therefore, the dynamical process are the following equations, as I told you, and above that, we put also passive variables like the aerosols and so on. So if you see that I put a schematic view of the model, you see that how it is complex. We have the wind, temperature, and humidity, which is the fundamental variables. It is changed with the advection, that the adiabatic process, which is very important. And that's why you cannot separate these equations separately. You cannot solve wind equation without a temperature. You cannot solve temperature equation without wind. You cannot solve the humidity equation without temperature and wind. So they are interrelated. So you have to solve the integrated manner. And these equations are nonlinear equation, so you cannot solve it by hand or tools like your laptop or small statistical methods, which can do actually with a laptop also. But this needs a very complex and huge modeling, computing system, so that the nonlinear equations you can solve simultaneously. Besides that, we have various physics in the atmosphere, like radiation, convection, diffusion, clouds, precipitation, orographic, gravity wave drag, and soil, snow, vegetation interaction. So these are the physical processes that we embedded in the model, because if you see here, so these are the, that elliptical things. They are your physics things, surface things, and the advection things. And these are the physical processes. They are also interactive. I show a schematic diagram of physical processes of like how cloudy form, how deep convection there, how shallow convection play a role, how the turbulence transport the heat, moisture to the atmosphere, and also main source is the energy from sun, which comes short wave radiation, earth emits a long wave radiation. So all these things are mountain, have a mountain drag. So these cover the all physics, and then we have aerosol and other things, they cover the chemistry. If we see simple plant plays a very important role because that is the vegetation and forest cover and so on, because it balances the radiation, the surface albedo and surface temperature and emissivity that depend upon the plant cover or the vegetation covers. Water balance, evapotranspiration is a very important thing. It comes the water from the root zone of the soil and then evaporate from plant leaves, and that is again comes from the evapotranspiration, which give the water vapor in the atmosphere. Rainwater interception are the leaf stomatal conductance and a runoff process where actually again plants play a very important role. The turbulence, the roughness, the leaf area index, that again depend upon the plants or vegetations. So therefore, it is not a that weather affect our biosphere or our agriculture, but our agriculture and plant cover or forest, they also affect the weather very severely and influence that. It covers all branches of the science, physics, mathematics, chemistry, biology, art science, environmental science, and computer science. Again, I don't have time, but I'll distribute this thing so you can go through that. Then we'll go to short-range prediction of extreme weather events. I will show some examples. The short-range prediction I will show because most important thing in most of our region is the tropical cyclones. So let us cover one aspect. But then if you go to cyclone prediction, we have also various ways, subjective methods and objective methods. Subjective methods are synoptic methods, persistence, climatology, and combined persistence and climatology climate. So these are the subjective methods. Then we come to that vortex, steering methods, satellite techniques, expert systems, statistical technique also there. Up to 1980 or so, we are all using statistical methods for prediction of tropical cyclone. But we cannot see that the evolution of the cyclone, intensification, decaying process, that is not possible in the statistical techniques. So therefore, we shifted over to numerical methods, and we have many numerical methods. More simpler were the steering flow method, where the atmosphere is a fluid and cyclone is a vortex. So vortex is moving with the wind. How the wind is moving, that gives the steering method mathematically. Similarly, we have integrated methods, we have barotropic and non-divergent methods, then we have gone to regional models, mesoscale models, and global models. Now we have come most important models like a high resolution coupled land, ocean, atmosphere, and wave modeling system. And India, in collaboration with our counterparts in other countries, we develop a new model that we call IOLA, Indian Land, Ocean, Atmosphere coupled modeling system, which is freely available. Anybody wants, they can integrate it. It covers the land, ocean, atmosphere. Then combine these dynamical statistical techniques to make the bias correction and so on, ensemble and super ensemble forecast, so that it will be done with one model with various combinations or multi-models, because models products we can get from different sources. Nowadays with the internet facility, you can get the model products from UK, from USA, from Japan, from China, and so on. Then you can make your own decision by coupling them and making it a probabilistic striking potential and probabilistic forecast of tropical cyclone also. So these are the development of the models. Schematically, it starts with the statistical method to that of the IOLA, that is what I told, Indian ocean, land, atmosphere coupled modeling systems. I am showing an improvement in tropical cyclone prediction. You may know that in the Bay of Bengal, we have a cyclone like Odisha super cyclone of 1999, where actually more than 10,000 people died. But almost a similar cyclone was in 2013, that is actually Falin, that also covered again Odisha coast near Berhampur. And there the casualty is only 20. And it is thanks to the improvement in the modeling system and observation platforms, so that actually we can get the better forecast, because you can see that the track, observed track, predicted track, they differ. But if you see that 2013, thanks to the IMD, constant efforts and so on, they have developed the models, improved the models in in collaboration with our counterparts from USA and UK. And now we have, you see that up to 7 days, 3 days to 4 days, even 5 days, it is striking potential is almost showing a point where it is going to hit the cyclone 3 to 4 days advance. And thanks to the disaster management authorities, they evacuate the people. Even in this case of Palin, more than 1 lakh people evacuated when we gave them the 3 days forecast that it is going to hit a specific point. But if you tell a broad region, it is very difficult to evacuate. So this is what shows that how best is improved the prediction of tropical cyclones, which damage not the loss of life, but the water resources, dams, floodings, and so on, and crops, and many other things. Because a cyclone suppose coming, you have to protect your crops. You may have to go to harvest, early harvest, if you know 5 days in advance. The impact of non-conventional data, I'll show very quickly. So this I'll show that how the data is important. And here you can see that if we take not many non-conventional data like Doppler radar and satellites, and take usual assimilation versus that of the including them, then you can see up to 5 days, the forecast drastically improves about by 37 to 40%. And this is how it shows that the 5 cases we have taken, like Nargis, which went to Myanmar, to Gonu, which have hit the these Gulf countries, and you can see actually the improvement. 24 hours is 22%, 48 hours is 31%, 72 hours is 41%, 96 hours is 47%, almost 50% you can improve in the 4-day forecast if we add more extensively, executively, the Doppler radar data and also satellite data in your assimilation process. Anyhow, these are statistics, and I am showing you one example for Bangladesh, that is Cyclone Sidar in 2007, November. And here, if you add the Calcutta Doppler radar, not add the Doppler radar, only one observation, that the Doppler radar of Calcutta, then you can see the difference that without that, it is not hitting. It is going here. And then it is improving, only the satellite is going here. But by putting Doppler radar, it goes the place where the cyclone really hit. The black is the hitting, and green one, the blue one is the prediction. So therefore, data is very, very essential for the prediction that you all know. And this is the statistics I'm showing for the several cases. And there you can see the 72 hours forecast improve when you put GTS data with Doppler radar data and all other data sets, almost 65% in several cases. That I show in one case. Similarly, we have done Palin, which I have shown you. We also predict that the pressure drop, actual pressure drop was about 940. The model gave 947. So you can see that how intense. And as I told you, 1 million people evacuated because of the IMD forecast. And this is the rainfall prediction. And out of that 20 people, about 10 people died due to rain far away from the cyclone in the northeast region in Mayurbhanj, that is this West Bengal and Odisha border, where in Subarnakha river we have the flood and where 10 people died. So these things can possible with the only numerical models. It cannot be done by the semantic methods. It's not possible. So this is also in addition to another casualty comes due to the sea level, the storm surges. Because storm surges make a coastal inundation, decrease the fertility of the fields, and also make that destroy the crops and so on. So this is also equally important, how much is the storm surges. So we have done a coupling that model with the storm surges. We get the peak storm surge about 3.3 meters. So coastal area up to 5 kilometers or so from coast, they are affected by storm surges. Similarly, another super cyclone of this century, that is Amphan, that crossed actually West Bengal and Bangladesh border, and it was 13 to 21st May. That also very well predicted. And here actually you can see that you can see that actually this is actually cone of uncertainty, and it is so that how the physics plays a role and all these things. And prior to landfall, we know that for the inner one, it is actually 80 to 90% probability. But whereas the outer one is maybe 30% probability. So the outer one can take a precaution, inner one should take evacuation. This type of prediction is possible, again, thanks to the supercomputer available, and thanks to the prediction system improved. And this is possible, and this all credit go to our India Meteorological Department, and they have a regional weather prediction, regional tropical cyclone prediction center in New Delhi, and they do all these things. Similar prediction of Dana, which is the most recent one in October 2024, where actually it was also predicted so nicely that the casualty was almost zero. Again, it's a probability, and this is the intensive probability, and predicted 4 days in advance. 22nd is predicted, 25th is going to landfall. And the present challenge in tropical cyclone prediction is the rapid intensification or rapid weakening of the processes. Coupling of the atmosphere with the ocean is the most important thing, because the energy comes in the cyclone when it is the ocean, and it comes due to sea surface temperature and so on. So this can be achieved by the coupling the ocean with the atmosphere. Similarly, land surface interaction is very important, because land surface, cyclones, once they cross land, they are affected by the plants, and we really make a thick plantation in the coastal area, because the plant will, due to friction, they will reduce the intensity of the wind, so that it will not interior place, it will affected less. And there is also shear vortex interaction that I'll show a little bit. But these are the things required. That's why thinking that we have developed a coupled land, ocean, atmosphere modeling system, so that the ocean is there. And when ocean temperature, as you know, SST, that is what we use in the most of the models, but that is actually, and beside that, sea or roughness is required. And when a cyclone passing through, due to upwelling in the ocean and some part downwelling, then we also get temperature change by 2 to 3 degrees, which is not normally occur. It is less than 1 degree. So that's why the fluxes, the energy in the upper layer of the atmosphere, they play very important role. Similarly, as I told you, land, it is not only the land as a friction, but it gives also the turbulence, and it gives also evapotranspiration and all these things, so that either increase or decrease the cyclone due to various ways. And when it is like, suppose in the USA, a cyclone like a hurricane, it crosses the land due to friction, it weaken, but once it move over the land, due to moisture supply, it may be intensified further. Like our monsoon depression, you know that monsoon time, monsoon depression, you move along a monsoon trough, and then we get a monsoon trough. If a monsoon depression is moving, that time we don't get cyclones, we get only depressions or low pressures. They sometimes intensify, and this low and depression, they develop in the Head Bay of Bengal, pass through whole entire Gangetic plain of India, crossing the many states, and again it may be intensified in the, when it go to the Rajasthan or Pakistan, that region, because it intensifies, again getting moisture feedback from the Arabian Sea. And that is sustained because the constantly low pressure system is available, that is monsoon trough. So these are the complex phenomena in the atmosphere, and to know that things, we have to go definitely a more accurate numerical weather predictions. And here I am showing you two cyclones occur in the same year. One is the November, one is that Palin, which I have shown you. In one case, it was very intensified, there's a rapid intensification there. One case, it weakened. Later, it is developed in November, 26th November, but it is crossed the land with only low pressure system as a depression. Because in one case, if you see Palin case, the intensity depends on the drop in the pressure at the center of the eye, and these are the observed points, the circle one, the model prediction. You see that it's showing that intensifying because the pressure is dropping at the center of the cyclone. And this is pressure is dropping and wind is increasing. Means low pressure and 10-meter wind. Similarly, in case of Leh, what is happening? The pressure is increasing as it moves towards land with the time, and as the pressure increases, the intensity of the cyclone decreases and wind is decreasing. So it will not become a cyclone or severe cyclone, it will become a low pressure depression. So this type of thing also up to 4 to 5 days in advance, the model can predict. So that gives that whether you have to go in a strategy of evacuation or protection of your crops and so on, or you can leave it because cyclone is one good thing, it gives up a lot of water. And for agriculture, we need the water. Particularly this cyclone Leh, which across the area, actually we have a less rainfall area in monsoon time because that is the region actually in south east peninsula region of Tamil Nadu and north Andhra Pradesh. But we get a lot of rain due to this cyclone layer, so it is supply the water for the irrigation during monsoon and post-monsoon time to go for the rabi crops and so on. It was useful. The cyclone has some good thing that it gives good rain, but it has a bad side that it gives heavy rainfalls, floodings, and wash out of this thing. And due to large storm surges, it also decreases the fertility of the coastal area surfaces. And because if you see the simulators, in case of the Palin, you have the constantly vortex is there from surface to that of the about 200 millibar. But in case of layer, the vortex is tilted. That I call the shear interaction. If a strong wind is coming on some level, then the vertical shear, vertical vortex, it becomes sheared, and that's why we don't get it intensified. Then I'm going to you for the medium range weather forecast, and you know that in our Southeast Asian countries, particularly the SAPAM countries, we have a place in India where we have a medium range weather forecast. And this needs global model, needs prediction up to 5 to 7 days, even 10 days now. And India, in this region, pioneered in medium range weather forecast, and we first developed the medium range weather forecast operational in the year 1994. We got a Cray computer, which is a supercomputer at that time, and it 1998, 99, 1988, 89, and we run it up to 4 or 5 years to customize for the Indian region, and then the model was become operational, and I was there at that time, the director research to make this model operational, and it was done on 1st June 1994. So since then, it has gone through tremendous improvements in the model as well as the computer facilities. We started with the Cray XMP, which is 4 megaflops, and now we have a supercomputers which have 7.49, 7.5 petaflops. So you can see that a tremendous increase in the computing. I will not go each one. Then we have different machines and so many IBM and Cray XC, and now we have the machine which can give us 7.5 petaflop. We have another machine in IITM. They do climate predictions and seasonal predictions. They have about 12.5 petaflop machine. Petaflop is about 10 power 16. So from 10 power 6 to 10 power 16, that is the operation, floating point operation per second. That computer has come, and this is for the computers that we got. And so we started with the TAT, which is about 150 kilometer resolution, to now T216, 1016, 1600 T1620, and that which gives us about 11 kilometers the resolution. And we have also now developed a Bharat model, that's again IITM team, which can go up to 6 kilometer resolution global model, which can integrate up to 10 days. And this is actually data is available, and this is what the agriculture community can extensively use, because when NCMW developed, its main purpose was their National Center of Media Weather Forecast for agro-meteorological advisories. That means agro-meteorological advisories is required for the planning, for the harvesting, for the water management, and for various agricultural activities. We need little longer time, not in costing alone for the short-term activities, but little longer time activities. Then from that, now with the supercomputer available in IITM, they have gone to the weekly, 2 weekly, up to 4 week forecast. That again, IMD also issuing, perhaps most of you may be knowing. And also they are using the seasonal forecast by taking the coupled land ocean atmosphere coupled global model, which gives them the seasonal prediction well in advance in a season and in a small scale of about 37 kilometer resolution, so that it can be used in a smaller scale. The statistical method, when we started it in India as a whole, then India has 4 subdivisions or 5 subdivisions, and now we are going as small as about 37 kilometers, and they have planned to go further improve it, and then you can go up to 25 kilometer resolution. That means you can get almost each district what will be the season. And you see last year the forecast was very accurate and it was very useful, and these things actually Dr. Pai will tell you, so I will not spend time for that. But I will show you that from 1994, when we improved the resolution of the model from T80 to the present day model, and we have substantially improved because we started with T80, which is about 150 kilometers. Then we have T70, which is 75 kilometers. Now we have the models which gives us T1533, which is 13 kilometers, and T1620, which gives us 12 kilometer resolution global model integrated for 10 days. And we have different type of data assimilation schemes. We started with 3D WAR. Now we have the 4D WAR data assimilation is operational. Now we have the weekly coupled ocean model also there. Previously we are taking for 7 days, we are taking ocean as a fixed SST, but now it is also assimilated ocean. So all these things have substantially improved the model. And as an example, I'm showing you the root mean square error of the wind at 850 million. That is about 1.5 kilometers. So you can see that that was the root mean square errors, which was 6 or so, 6 to 7 meters per second, and now it is reduced to 4 meters per second. So there is a substantial increase of the improvement in the prediction system in this about 30 years time. And last year they celebrated 30 years because now we are at par with any global models in the world. In USA NCEP or UK Met Office or ECMWF, who is the premier organization world over, and we are at par with the forecast, and these products are available, and these products can be available to all of you, and I think it is SAFOM and Government of India together, they can help you that you can get this type of high resolution rainfall, temperature, wind, and so on, well in time up to day 1, day 2, day 3, day 4, day 5, up to day 7. And weather prediction means you get a particular day and particular time. You may need today, 3rd day, morning time, what will happen, 3rd day, afternoon, what will happen, 3rd day, evening, what will happen, that you can get. But when you go 10 days or beyond, or 7 days or beyond, then we go for pentile scale forecast, which gives average. This pentile is going to be heavy rain or dry spell. Second pentile is going to the heavy rainfall, or fourth pentile is going to, that is what we call mean, that is climate. Similar seasonal forecast cannot be done for a particular day. I cannot tell what will happen after 30 days or 31 days or 34th day or 90th day. But it can give that what will be the mean rainfall distribution over the region at the resolution of 37 kilometers, and also it can give it as a climatological mean type. It mean, and it will give us an anomaly. That means it will tell that this monsoon season is going to have an excess rain season, or the June is going to have an excess season or deficient season, or July, August, and September. If they tell that this is going to be July and August, then actually you know that is the time when plant needs more water, then you can plan your activities. Or if less rainfall, you can plant the crops which needs less water. But if excess one, you can plant which needs more water, like a flooding year, flood year, deficient year, and which month they can go. Month-wise, they can go. Winter-wise, and for the day-to-day activity, you can go to short and medium range scale. They get data from various sources, and you see that the data is the backbone, I told you, and they get data from IMD, from ISRO, from NOAA, from GTS, from European satellites, and Chinese satellites, and Korean satellite, and so on. So data comes from various systems because we always hungry for the data. The more we get data, we can get better the initial conditions. Better initial condition means our model will better improve the prediction. So therefore, these are the satellites that is developed, and now we have come to era we call that satellite we have launched, that is we call that is NASA ISRO command satellite, satellite which give the soil moisture and water, that is NISR we call, NISR. So SR, NISR, this NISR satellite gives you, that is a joint satellite launched by NASA and ISRO of India, and this satellite, the SAR radar is there, so it can give the groundwater contents, it can give the soil moisture to some extent, snow cover, and so on, which is very, very essential observation systems that can be useful for improving the model, improving the practice of the its utilization, and also getting the strategies appropriately. Impact of the observations on 24 hours global forecast. At NCMWF, you can see that if you have one data, other data, how it is improving, then when you put all the data, there's a lot of improvement taking place. Similarly, this is a comparison of the 25 years model forecast for the period from 1999 to 2023. This shows that T82, that of the present day 12 kilometer model of the geopotential height, 850 millibar. Sorry, this is the wind of 850 millibar against that of the over the Indian region. That is the global region, this Indian region, forecast accuracy in terms of root mean square errors of wind and the 850 HPA pressure level from day 3 forecast generated by different operational global models of NCMWF in last 25 years. Then you can see that the root mean square error is substantially decreasing, as I show you there. And so also, this is a comparison of the different models. Because we have global models, not only India, we have global models in Australia, we have global models in China, we have in Korea, we have in Japan, USA, CMWF, and so on. So this also gives an inter-comparison of the performance in models. That is again a project of the WMO to make available of this type of products. This is day 3 forecast accuracy of 500 HPA geopotential across the northern hemisphere, it average over the entire northern hemisphere, highlighting that the NCMWF model aligns closely with the other global deterministic models for leading in the as one of the leading methodological center for weather prediction. So these are the things I am showing because the data is at your store, your doorstep, and you can take help of this SAFM, and fortunately IMD and NCMWF and IATM they are at the doorstep to help you. So those who are interested in the SAFM regions and so on, or even global region, you can contact them through SAFM and you can get this type of data. And India is also lead in agrometeorology that you know, then you can use those things for your agricultural practices. And finally, we want the city-based forecast, because now we know that climate forecast city scale also quite important, and we also need a decision support system, because that is the impact-based forecast, and the end users, they want a decision support system. They want what to do and what not to do. So that is again possible with integrating the GIS, remote sensing, and also city mapping and the height of the buildings, lanes, and so on for air quality and the other things, or even the vertical farming, that what is done in the city in the top of the roof, that can also need some weather forecast, and this decision support system is done for smaller area. And I can show you that keep time is there. You see the land use, land cover, this is city Bhubaneswar, where it is changing, because this is again project we have done together to develop a decision support system. And if time is there, I can take 5 minutes, otherwise I will stop here. So I can continue 5 minutes. Okay. So you see, this is I'm showing like a city, and where actually I born and brought up. And this is a city where I'm working also now, and with IIT Bhubaneswar and SOA University. So what we have done, first from the satellite, we saw like how city is grown in time. So this is the period from 1980 to that of the 2020. Every 10 years gap. 1980, this was the city cover, that red one you can see, and then it is increase. Now this is how the city is built up area. So that increase about now 13 times increase the city. So obviously we have a lot of tall buildings. The greenery things are decreasing, city is increasing, and the population also equally increasing in this time. So this have a tremendous impact. Why population have impact? Because you have more vehicles, more human activities, and so on. And so human activities, city growing, city, and as you know, now world over, about 54% of our population, they are staying only 5% of the area that is city. City is a very small area, but it is thickly populated. So the population density is increasing, building area is increasing, forestry and other things is decreasing. So as a result, it's a tremendous effect. And now we know that many cities we have, particularly India, I know, and you may have also in your own countries, most of these cities, they are getting very short period, heavy rainfalls, long time, no rainfall, like in the cold region. That is the impact of the climate change also partly, and along with the building of areas. So here what we have done, we have taken a couple model, but resolution we have taken half a kilometer. So if you see the outer one is 4.5 kilometers, this area, domain 1, this is WRF model. Second domain is 1.5 kilometer, and the city of Bhubaneswar and around have taken 0.5 kilometer. That means sub-kilometer region, it is only 500 meter scale. But we have planned, NCW have gone to 330 meters, and we have planned also, even possible, we can go further down. So you can get final resolution forecast for the city regions. So this I am showing how it is performed. Global model versus that of the sub-kilometer model. So this is the example of, we have done it almost semi-operational basis for the 2022. And Bhubaneswar, we have this is the stations we have. We have only few stations, 15 engaged stations are there. And we have about 23 cases of heavy rainfalls. And rainfall more than 7 centimeters or so. So here you can see that this is the blue one. It is shown from the global models, and the red one that shows it from the half a kilometer resolution model with a WRF. Overall, you can see that it is 80%, this is 20%. Day 1, day 2, up to day 3, because it is mesoscale model, so we have run up to 3 days. So you can see that how dramatic improvement comes if you put the city morphology in the models and city land covers and make very high resolution, because if you take 11, 12 kilometer resolution, then city have a hardly 1 or 2 points. Because city of suppose 50 kilometer by 50 kilometer, 12 kilometer resolution, you get 4 by 4. But here you get half a kilometer, you get hundreds of points and more refined points. So your forecast is improved dramatically if you go from a domain. This is the overall forecast of 4 days, 3 days, and day 1, day 2, day 3. Similarly, lead time also improved drastically. Overall, day 1, day 2, day 3. So an event capture at a specific station, because you see that the rainfall sometimes occur at one place, not in other place. So that type of capture also quite good. And the magnitude of the rain, our model, like the half a kilometer model, it shows a little overestimate, whereas the global model, it shows the underestimation. So these things also we have done in several cities. And here we have done from Pune, we have done from Bangalore and so on, but I am showing the Bhubaneswar. And this diagram shows that all these 23 cases, and where actually the black one is the actual occurs, and the that is observed one is the red one, the WRF is the blue one, the black one is the IMD-GFS. So you can see that, again, you can see that the magnitude also quite well represented in these systems, and the number of success events for the cities, success is 67%, and failure is false alarm is 33%, whereas the global models, because being it a very low resolution models, obviously the 12 kilometers is now a low resolution we feel, because we have half a kilometer models. So that you can see the success rate is in the global model is decreases because of the coarse resolution, and microscale process are not built up for the capturing the city, and city structure, morphology, and other things are not there. So therefore, forecast decreases. So therefore, we have to have different set of models, global models, regional models, and region-specific models required with very high resolution, with more details, more microphysics, and so on, so that it can improve. So this is just I'm showing the example. Similar the heat wave situation, that also we see that land cover impact on the heat wave is quite dramatic. So we can predict also heat wave, and which has the stress, thermal stress of the plants, that also can be predicted significantly better than that of the coarse models. So with this, I stop here, and thank you very much.